What's going on? So far, we have talked about, actually, what kind of work have we talked about? We talked about kinetic energy or potential energy. I think it was kinetic. Oh no, we just talked about force equals work, or work equals force times distance. And this thing is going to also talk about kinetic energy. Okay, all right, cool. So, what we've talked about so far is work equals force times distance, right? We're talking about work. If I were to graph that, that would be, if I were to apply a force here, and it acts over a certain distance, d, and I'm applying a constant force across it, then what is your work, the amount of work you did? If I apply a force F over a constant distance d, and it's a constant force F, then what is my work? Well, my work is equal to force times distance. It's actually the area inside of this curve. Do you see that? Does that make sense? Julia?
Yeah.
All right, cool. Now, here's the thing about springs. And I think the best thing to do would be to actually see a spring. So if you have a chance, go and grab a ballpoint pen. And I'll kind of talk while you're grabbing a ballpoint pen. If you don't have one, don't worry about it. And take a part of that ballpoint pen and you have a spring inside there. Actually, maybe, you know what, don't worry about going and grab a ballpoint pen. Just kind of imagine the spring, okay? Now, a spring energy, we also call that elastic energy. And we denote it with this little squiggly line like that. Represents a spring. Now, say that I have a spring that's attached to a box, and I take this box and I move it like that. Now, what's going to happen is this spring is going to stretch and stretch and stretch. Now, here's my question, is if this spring is just hanging out and you put your hand on top of it, do you feel any force that this spring is pulling? Or like, I haven't pulled the box. Do I feel any force acting on this box? I'm just resting my hand on it. Julia?
Say that again.
All right, yeah, you're looking for a ballpoint pen. If I put my hand on top of it and I'm just resting there, is the spring pulling against my hand?
No.
No, because the spring is at a relaxed length, okay? Now, as I move this thing out, the spring will pull a force on me, against me. Does that make sense?
Yeah.
Now, if I move this thing out a lot, this spring will pull a force against me. Here's my question is, if I have the spring out here, or if I have the box out here versus if I have the box out here, which one will pull, which will the spring pull with a greater force? When it's stretched out to here, or when it's stretched out to here?
When it's stretched out really far.
Yes, exactly. And we call that a variable force because the force changes as it, the force will change as you move further and further away, right? So that's where you have a variable force. So the amount of force that you feel depends on the distance that you are away from its relaxed length, okay? So we measure that relaxed length and we call it x. And so we say force is equal to k times x. And this k is actually called Hooke's constant, H-O-O-K-E. Hooke's constant. And it's just a number. Or actually, no, it's not just a number. It's some kind of scaling factor. But it's measured in newtons per meter. So it would be like 5 newtons per meter. Does that make sense?
Yeah.
Because if x is measured in meters, like 2 meters or something like that, you want the meters to cancel out, and that's going to equal to a force, so you'd have like 10 newtons. So apparently, for a 5 newton per meter spring, if you move it 2 meters, the force you would feel is 10 newtons. Does that make sense? Am I speaking crazy here? Or does,
No, I get it.
all right. I actually vaguely even remember teaching this to you a little bit when we talked about forces. I talked to you about spring forces. If not, then this is pretty much it. That's spring forces. Technically, you need a negative out in front there. But that's really just for sign purposes. Because the reason why there's a negative over there is because if I pull this thing in a positive x direction, which way is the force going to be pulling? Which way is this box going to be pulling against me?
Oh, in the opposite direction.
It's going in the opposite direction. If I push this box in the negative direction, which direction is the force going to be pushing?
It's going to be pulling.
Oh, if I push it in like this, then the spring's going to want to push the box out like this.
Right.
Now if I pull it out like this, the spring's going to want to pull it back. That's why there's that negative out in front, because it's always accounting for that opposite reaction. Does that make sense?
Yeah.
Okay. If I were to graph this equation right here, this line, it would look like this. It would just be a simple line like that. Does that make sense?
Yeah.
And this graph would be f is equal to kx. So whatever x you're talking about, you move up a height kx. So what I want to do is I want to figure out how much work I'm going to be doing if I move a spring. Now how much work I'm going to be doing if I move a spring, on the other hand, is, well, that's the area underneath this curve right here. Well, what's the height of this thing? That's kx. Does that make sense?
Yeah.
And what is the length of this thing? That's x. So my force times distance, the force is kx, the distance is x, but I also need to put a 1/2 out in front. Where does a 1/2 come from?
Well, it's a triangle shape, so it's half of the
Half base times
normal
height.
square
Perfect.
area.
Exactly. It's 1/2 base times height. That's what my area is. So the work on a spring is equal to 1/2 kx squared. Are we cool with that?
Yeah.
So that's how much work. This is the equation for work when we're talking about a spring. If we're talking about a force, we're talking about kx. But if we're talking about a spring, we're talking about kx squared. We cool?
Yeah.
By the way, Julia, what math are you in?
AP calculus.
Calculus. Okay, so you've taken derivatives.
Yeah.
I kind of want to show you this. This isn't necessarily required, but if you take the derivative of the energy, you'll always get the force back. Take the derivative of this with respect to x.
Take the derivative of the work.
Yeah. So d dx, or partial w partial x, of this is just, you drop down the 2, right? And you get 2 over 2 kx.
Oh, so basically the rate of change of the work is the same thing as the force.
Yes. Yes, exactly. But this is not a calculus-based physics course, even though most physics is, or all physics is calculus-based. This is trigonometry-based, so I didn't need to show you that, but that's really where it comes from.
Well, I mean, I was doing Khan Academy, and if you take the derivative of, distance, then you get velocity, and if you take the derivative of velocity, you get acceleration.
Yeah. In fact, that's where we got the derivatives from, is because Newton came along and said, hey, I've got this whole new science called physics that deals with distances, velocities, and acceleration. And then they said, you're crazy, you don't know what you're talking about. So he went back home and wrote Principia Mathematica and basically invented calculus so that he can prove physics.
That's cool.
All right. So anyway, that's the work done by a spring. Let's do an example problem and see how we can apply this thing. Cool?
Yeah. See, I understand the formulas. It's just when I tried to apply it to the problems, it ended up not coming out with the right answers.
So that could be two things. It could be I just did the problem wrong, or it could be